So I will be basically talking about electroweak phase transition, a simple model with PNGB dark matter. So this is the brief overview of my talk. I will first introduce the model, and then I will state the requirements for studying phase transitions, and then move on to effective potential at finite temperature, and then study the phase transition, comment on some benchmark points, and briefly discuss the DM phenomenology associated with it, and finally go to the gravitational wave signature with corresponding to those benchmark points. Okay, so it is generally believed that the universe has undergone through many phase transitions, and we see that if these cosmological phase transitions are of first order in nature, they give rise to a stochastic gravitational wave background, and this gravitational wave has the information of the early universe. So, motivated by this, we study the phase transition and the gravitational waves. And the model, one simplest model we have taken with the pseudo Nambu Goldstone model, where we have, apart from the standard model Higgs, we have two other scalar fields, the phi, which is real scalar, and another field which is the S, which carries Z3 charge and transforms under Z3 symmetry as S goes to e to the power e2 pi I by 3s, and phi has an odd Z2 charge. However, it is invariant under the Z3 symmetry. So this is the structure of the tree level potential, where we have considered all the terms and the Z3 symmetric terms, and this mu3 will play a crucial role in determining both the DM phenomenology and the strong first order phase transition. So in inotary case, after the electroweak symmetry breaks, the scalar fields are parameterized in the following manner, which is given by equation 2, where VH, Vs, and V5, both are, three of them are assumed to be real quantities. And now we go to these CP even scalar fields with mix with each other to form the three physical mass eigenstates H1, H2, H3. And for simplicity, we have this is just a choice that we have made, kept in throughout our analysis, the mass of H3 to be greater than H2 to be greater than H1, and we identify this H1 as the standard model Higgs having mass 125 GeV and have the wave around 246 GeV, and it is consistent with all the experimentally measured values of the standard SM Higgs at the LHC. So requirements of the studying for the phase transitions is the Coleman-Weinberg potential, which is the at zero temperature, and also in the finite temperature, which forms the total complete effective potential, which is given by the equation 6. This V0 is the tree level effective potential, or tree level potential, the classical part. The CW is the one loop Coleman-Weinberg potential at zero temperature. VCT is the counter terms associated with it at zero temperature, and VT is the thermal thermal corrections to the effective potential. So we first compute this Coleman-Weinberg potential and the Landau gauge using the MS bar scheme, which is given by the expression 7, where these Nij are the degrees of freedom for all the physical particles. This Cj's comes from the renormalization constants, and this is equal to 3 by 2 for scalars and fermions, while 5 by 6 for the vector bosons, gauge bosons. And this Fi is 0 for bosons and 1 for fermions. So it may happen that while introducing the Coleman-Weinberg potential in the tree level part, the masses and the waves may change. So in order to ensure that those does not change in the zero temperature, we incorporate these counter terms, this delta mu h square, delta lambda h, and this one. Now calculating these counter terms require the condition that the first derivative of the delta VCT plus delta V, which is the entire which is the effective potential at zero temperature, deducted from the effective potential at zero temperature minus the classical part of the potential, and this double derivative will and also this double derivative part, because this will ensure the waves to be intact, this will ensure the masses to be intact. Okay, now taking into the thermal effects, the temperature dependent part of the effective potential is given by this quantity, where this JB and JF are the bosonic and fermionic integrals given by this expression, and one can expand in terms of m by t. Now this approximation is not valid every time. For there is this polynomial expansion is valid for certain regions, but we just I have, for the sake of complexity, I have shown that, but in my analysis I have used this entire expression. So this is the structure of how the effective potential varies with the scalar field. The pictorial representation, if it is second order phase transition A and first order phase transition B. So initially, when temperature is greater than a particular temperature, which is known as the critical temperature, so the wave was at 0, but as the temperature of the universe cooled down, we can see that it smoothly changes without formation of any barrier. This kind of transition is called second order phase transition. And if there is a barrier formation, then the TC is the temperature at which we have degenerate minimas. So if the barrier formation takes place and when the universe is cooling down, then we say that we have a first order phase transition. So this barrier formation is necessity for the production of the gravitational waves. So the critical temperature is calculated using the condition that V at H high, that means the wave at high phase. High phase means before the transition, the value of the wave, comma Tc, and V at H low, comma Tc. So we define another quantity, which is the order parameter, which is the difference of the waves at high and low temperatures divided by the critical temperature. If this quantity is greater than equal to 1, we say that the phase transition is strong along that particular field direction. Otherwise, we say that the transition is weak. Now, for first order phase transition actually involves two key temperatures. One is the critical temperature, which I told before. Another is the nucleation temperature. The phase transition actually, which is typically lower than this TC. So this transition actually proceeds through bubble nucleation, and the probability per unit volume, per unit time of tunneling from the false of the field from the false vacuum to the true vacuum is given by this expression. And where S3 is the three-dimensional Euclidean action, and these waves actually follow this differential equation, which is nothing but the Euler-Lagrange equation coming from this action 16 with the given boundary condition. And the nucleation temperature is then defined as the temperature in which this following condition is satisfied. Roughly, we can say that nucleation temperature is also the temperature at which one bubble of the true vacuum is produced in one Hubble volume, roughly speaking. But mathematically, in most of the cases, we use this expression. Okay, so we have found 7 benchmark points where we have got strong first order phase transitions, which is S of PT. So benchmark point 1, 2, 3 have strong first order phase transitions along SM directions and BSM Higgs directions, all of them. But 4, 5, 6, 7 only have strong first order phase transitions in the BSM Higgs direction. So this is a pictorial representation of benchmark point 1, where we have the H1 field with the evolution of the wave of H1, H2 and H3 with temperature. So whenever we see a color change, we conclude that there is a phase transition, and arrow is there. If the color changes, it means a phase transition occurred. If there is an arrow corresponding, we say that it is the first order. If there is no arrow, it is the second order. So so here we see all of them, in the H1, H2, H3, all of them has first order phase transition. Now whether they are strong or not depends on the zeta value, which can be calculated using the del Hi by Tc condition. The Tc is here in the 124.78 GeV, and Tn is 124.65 GeV. So these are the some role of the model parameters where the MH3 and MH3, V5 and this sin alpha 2, which alpha 2, these three are the main parameters, means which influence the strength of the phase transition along the SM Higgs direction. And another representation is that this is another corresponding to another benchmark point where the strong first order phase transition is only along the BSM Higgs direction. Here you can see the SM Higgs direction has no first order phase transition, the wave is continuous and the color change is without any arrow. Okay, so now coming to the DM phenomenology, to quantify dark matter abundance, we define this fudge factor Fi, which is given by the obtained relic density divided by the observed relic density, which is around 0.12. So if the imaginary component of the S field is a DM dark matter candidate, we can say that our model also explains the dark matter phenomenology. Now, if Fk is less than 1, the predicted model, the model predicted relic density is suppressed compared to that observed value of Fk, which is around, which is 1 for for larger scalar, which is near to 1 for larger scalar sector couplings. So these are the corresponding dark matter observables, direct detection, cross section, and relic density corresponding to 7 benchmark points. We can clearly see that the latest Lux Zeppelin 2024 result excluded the BP 2, 3, and 7 points. So we only want 4, 5, 6 of the remaining points where we can have strong first order phase transition along with the dark matter dark matter relic density and direct and indirect directions all satisfied. So this is just a pictorial representation of which parameters have the most important influence on the dark matter relic density and direct direction cross section, mainly the VS parameter. And so the gravitational waves, so the first order phase transition can also act as a source of primordial gravitational waves, which can be of there are three mechanisms, which can comprise of three mechanisms, which is the bubble collisions of the bubbles of the collisions of the true vacuum, which collide with each other, the sound waves propagated generated when the bubbles are colliding, and the magnetohydrodynamic turbulence which are generated in the plasma. So this total energy spectrum of GW is expressed as this equation 20, which is the collision, sound wave, and the turbulence terms. Which is this GW spectrum is primarily shaped by 4 key parameters, which is alpha, beta, Tn, and VW. So bubble wall velocity is VW, Tn I defined earlier. This alpha is related to the latent heat evolved in the phase transition, and somehow also denotes how strong the phase transition is, and is given by the equation 21, while this beta by Hn is represents the ratio of the inverse time duration of the total phase transition to complete, evaluated at all evaluated at the temperature Tn. Now this GW spectrum is defined as 1 by rho c, the logarithmic derivative of this rho GW, where this rho GW is the energy density of the stochastic background, and rho c is the present value of the critical energy density of the universe. This rho GW we can find from Einstein's equations that it has this expression, where H, AB are the two modes of polarization. And so the results we got for the 4 benchmark points fall in the ultimate Desigo region, and we got significantly low peaks because we had to also consider the dark matter direct direction cross section to be below the Lux Zeppelin bound latest. So that made this result slightly bad. So ultimately, we can comment that the study investigates dark matter and phase transition dynamics in a model featuring PNGB within a Z3 symmetric complex scalar and a Z2 symmetric real scalar. So two patterns, as I mentioned, are observed in the phase transition. One is along SM directions and another is along BSM directions. Certain benchmark points are excluded from the Lux Zeppelin constraints. The mu3 present in the tree level part of the potential actually facilitated the phase transition because it creates a barrier even in the tree level, and also it plays a vital role in the dark matter physics because it is related to the VS parameter. Now the analysis of this GW spectrum indicates the highest amplitude coming from the points which are only along BSM Higgs direction, and these findings enhance our understanding of the early universe and suggest potential GW observers for testing phase transition dynamics within this theoretical model. Thank you.
Thank you, Koustav. Questions?
Yeah. Thanks for the nice talk. So your theory has a discrete symmetry, and you are giving.
Wall.
Yeah.
Yeah. So actually, the point is our theory has some discrete symmetry, but eventually we can evade the domain wall problem by gauging the Z3 symmetry. That means we say that the Z3 symmetry comes from some continuous symmetry, and then we have the Z3 symmetry. Otherwise, I have to calculate those surface
In
tension.
that case, how do you observe the gravitational waves?
This coming from phase transitions. See, that I have not done, but we can say that if the Z3 symmetry is coming from some continuous symmetry, which is higher than that, then there is no question of domain walls arising, because initially it is not
No,
discrete.
there will be wall bounded by strings, and in your case it's GT symmetry, so that wall will dominate.
That I don't know about the strings, but in my opinion, if you have a wall, if you have a continuous symmetry, and so initially, if you have a continuous symmetry to begin with, you don't have any domain wall. Then it can break towards
No. If you have like then Z3 will be a subgroup of
yes, of that
symmetry.
continuous symmetry.
And if you break Z3, there will be a wall connected to the string. There will be each string will be get connected by 3 walls. So again, in that case, there will be.
Yeah, but
domain wall
I
problem.
don't have any idea about those strings actually. I didn't investigate that.
No. In that case, actually, your gravitational wave may be suppressed, or if you want to,
That means you are saying that the GW from coming from those strings
there will be like domain wall problem. In fact,
the cosmological problem.
yeah.
Although that I haven't
You
investigated.
have to find out some way to get it out, because you are assuming that the symmetry breaking is actually happening. This Z2 symmetry break, Z3
Z3.
symmetry breaking.
Yes. Okay, I will look into that. But yeah, in our work, I have said that it coming from a continuous symmetry. Maybe.
We'll go back to the audience for more questions. If there are more, then we can come back to it. Are there any more questions? Yes.
Could you just sum up quickly for a layman why the the space transition along the non-standard model Higgs direction gives you a much larger signal for the gravitational waves, please?
So that's an observation I found. The main physics behind that maybe because see, I have to also keep that in mind, and that I have to match the direct direction cross section in the dark matter sector. So that is what is making the lambda HS couplings. So what happens? That means to get the high Rayleigh density, I have to consider the VS, the wave of the complex scalar, to be means high, which is making the lambda HS low. And in another case, what I have to do, if the lambda HS is high, that will cross the direction bound. So what happens that again, to get a strong first order phase tension, I need quite high, reasonably high coupling constants, which are within the perturbative bound. So that makes some couplings stronger than the other, and which we observe that along the PSM directions, the suppression is low. This is just an observation. Yeah.
Okay. Do you still have questions? All right. Are there any more questions from the audience? Christoph, are you going to? All right. If there are no more questions, Anish, I think we can close the session. If you have any final announcements.